In theoretical physics, the renormalization group refers to a mathematical apparatus that allows systematic investigation of the changes of a physical system as viewed at different distance scales. In particle physics, it reflects the changes in the underlying force laws as the energy scale at which physical processes occur varies. Energy, momentum and resolution distance scales being effectively conjugate under the uncertainty principle. A change in scale is called a scale transformation. The renormalization group is intimately related to scale invariance and conformal invariance, symmetries in which a system appears the same at all scales. As the scale varies, it is as if one is changing the magnifying power of a notional microscope viewing the system. In so-called renormalizable theories, the system at one scale will generally be seen to consist of self-similar copies of itself when viewed at a smaller scale, with different parameters describing the components of the system. The components, or fundamental variables, may relate to atoms, elementary particles, atomic spins, etc. The parameters of the theory typically describe the interactions of the components. These may be variable couplings, which measure the strength of various forces, or mass parameters themselves. The components themselves may appear to be composed of more of the self-same components as one goes to shorter distances. For example, in quantum electrodynamics, an electron appears to be composed of electrons, positrons and photons, as one views it at higher resolution, at very short distances. The electron at such short distances has a slightly different electric charge than does the dressed electron, seen at large distances. And this change, or running, in the value of the electric charge is determined by the renormalization group equation. History. The idea of scale transformations and scale invariance is old in physics. Scaling arguments were commonplace for the Pythagorean school, Euclid and up to Galileo. They became popular again at the end of the 19th century, perhaps the first example being the idea of enhanced viscosity of Osborne-Reynolds, as a way to explain turbulence. The renormalization group was initially devised in particle physics, but nowadays its applications extend to solid-state physics, fluid mechanics, cosmology and even nanotechnology. An early article by Ernst Stueckelberg and André Peterman in 1953 anticipates the idea in quantum field theory. Stueckelberg and Peterman opened the field conceptually. They noted that renormalization exhibits a group of transformations which transfer quantities from the bare terms to the counter terms. They introduced a function h in quantum electrodynamics, which is now called the beta function. Murray Gell-Mann and Francis E. Lowe in 1954 restricted the idea to scale transformations in QED, which are the most physically significant, and focused on asymptotic forms of the photon propagator at high energies. They determined the variation of the electromagnetic coupling in QED, by appreciating the simplicity of the scaling structure of that theory. They thus discovered that the coupling parameter G at the energy scale μ is effectively given by the group equation for some function G and a constant D. In terms of the coupling G at a reference scale m, Gell-Mann and Lowe realized in these results that the effective scale can be arbitrarily taken as μ, and can vary to define the theory at any other scale. The gist of the RG is this group property. As the scale μ varies, the theory presents a self-similar replica of itself, and any scale can be accessed similarly from any other scale. By group action, a formal, transitive conjugacy of couplings in the mathematical sense. On the basis of this group equation and its scaling property, Gell-Mann and Lowe could then focus on infinitesimal transformations, and invented a computational method based on a mathematical flow function psi equals GD, of the coupling parameter G, which they introduced. Like the function h of Stueckelberg and Peterman, their function determines the differential change of the coupling G with respect to a small change in energy scale μ through a differential equation, the renormalization group equation. The modern name is also indicated, the beta function, introduced by C. Callan and K. Szymanczyk in the early 1970s. Since it is a mere function of G, integration in G of a perturbative estimate of it permits specification of the renormalization trajectory of the coupling, that is, its variation with energy, effectively, the function G in this perturbative approximation. The renormalization group prediction was confirmed 40 years later at the LEP accelerator experiments. The fine structure constant of QED was measured to be about 1/127th at energies close to 200 GeV, as opposed to the standard low-energy physics value of 1/137th. The renormalization group emerges from the renormalization of the quantum field variables, which normally has to address the problem of infinities in a quantum field theory. This problem of systematically handling the infinities of quantum field theory to obtain finite physical quantities was solved for QED by Richard Feynman, Julian Schwinger and Shinichiro Tomonaga, who received the 1965 Nobel Prize for these contributions. They effectively devised the theory of mass and charge renormalization, in which the infinity in the momentum scale is cut off by an ultra-large regulator, lambda. The dependence of physical quantities, such as the electric charge or electron mass, on the scale lambda is hidden, effectively swapped for the longer distance scales at which the physical quantities are measured, and, as a result, all observable quantities end up being finite, instead, even for an infinite lambda. Gell-Mann and Low thus realized in these results that, while, infinitesimally, a tiny change in G is provided by the above RG equation given psi, the self-similarity is expressed by the fact that psi depends explicitly only upon the parameter of the theory, and not upon the scale mu. Consequently, the above renormalization group equation may be solved for G. A deeper understanding of the physical meaning and generalization of the renormalization process, which goes beyond the dilatation group of conventional renormalizable theories, came from condensed matter physics. Leo P. Kadanoff's paper in 1966 proposed the block spin renormalization group. The blocking idea is a way to define the components of the theory at large distances as aggregates of components at shorter distances. This approach covered the conceptual point and was given full computational substance in the extensive important contributions of Kenneth Wilson. The power of Wilson's ideas was demonstrated by a constructive iterative renormalization solution of a long-standing problem, the Kondo problem, in 1974, as well as the preceding seminal developments of his new method in the theory of second-order phase transitions and critical phenomena in 1971. He was awarded the Nobel Prize for these decisive contributions in 1982. Meanwhile, the RG in particle physics had been reformulated in more practical terms by C. G. Callan and K. Szymanczyk in 1970. The above beta function, which describes the running of the coupling parameter with scale, was also found to amount to the canonical trace anomaly, which represents the quantum mechanical breaking of scale symmetry in a field theory. Applications of the RG to particle physics exploded in number in the 1970s with the establishment of the Standard Model. In 1973, it was discovered that a theory of interacting colored quarks, called quantum chromodynamics, had a negative beta function. This means that an initial high-energy value of the coupling will eventuate a special value of mu at which the coupling blows up. This special value is the scale of the strong interactions, mu equals lambda QCD, and occurs at about 200 MeV. Conversely, the coupling becomes weak at very high energies, and the quarks become observable as point-like particles, in deep inelastic scattering, as anticipated by Feynman-Bjorken scaling. QCD was thereby established as the quantum field theory controlling the strong interactions of particles. Momentum space RG also became a highly developed tool in solid-state physics. But its success was hindered by the extensive use of perturbation theory, which prevented the theory from reaching success in strongly correlated systems. In order to study these strongly correlated systems, variational approaches are a better alternative. During the 1980s, some real space RG techniques were developed in this sense, the most successful being the density matrix RG, developed by S. R. White and R. M. Nowak in 1992. The conformal symmetry is associated with the vanishing of the beta function. This can occur naturally if a coupling constant is attracted, by running toward a fixed point at which beta equals 0. In QCD, the fixed point occurs at short distances where G0 and is called a ultraviolet fixed point. For heavy quarks, such as the top quark, it is calculated that the coupling to the mass-giving Higgs boson runs toward a fixed non-zero infrared fixed point. In string theory, conformal invariance of the string world sheet is a fundamental symmetry. Beta equals 0 is a requirement. Here, beta is a function of the geometry of the space-time in which the string moves. This determines the space-time dimensionality of the string theory and enforces Einstein's equations of general relativity on the geometry. The RG is of fundamental importance to string theory and theories of ground unification. It is also the modern key idea underlying critical phenomena in condensed matter physics. Indeed, the RG has become one of the most important tools of modern physics. It is often used in combination with the Monte Carlo method. Block spin. This section introduces pedagogically a picture of RG which may be easiest to grasp. The block spin RG. It was devised by Leo P. Kadanoff in 1966. Let us consider a 2D solid, a set of atoms in a perfect square array, as depicted in the figure. Let us assume that atoms interact among themselves only with their nearest neighbors, and that the system is at a given temperature. The strength of their interaction is measured by a certain coupling constant. The physics of the system will be described by a certain formula, say. Now we proceed to divide the solid into blocks of squares. We attempt to describe the system in terms of block variables, i.e., some variables which describe the average behavior of the block. Also, let us assume that, due to a lucky coincidence, the physics of block variables is described by a formula of the same kind, but with different values for n. Perhaps the initial problem was too hard to solve, since there were too many atoms. Now, in the renormalized problem we have only 1/4 of them. But why should we stop now? Another iteration of the same kind leads to, and only 1/16 of the atoms. We are increasing the observation scale with each RG step. Of course, the best idea is to iterate until there is only one very big block. Since the number of atoms in any real sample of material is very large, this is more or less equivalent to finding the long-term behavior of the RG transformation which took n. Usually, when iterated many times, this RG transformation leads to a certain number of fixed points. Let us be more concrete and consider a magnetic system, in which the J coupling constant denotes the trend of neighbor spins to be parallel. The configuration of the system is the result of the trade-off between the ordering J term and the disordering effective temperature. For many models of this kind there are 3 fixed points. And this means that, at the larger size, temperature becomes unimportant, i.e., the disordering factor vanishes. Thus, in large scales, the system appears to be ordered. We are in a ferromagnetic phase, and exactly the opposite temperature dominates, and the system is disordered at large scales, a non-trivial point between them, and, in this point, changing the scale does not change the physics, because the system is in a fractal state. It corresponds to the Curie phase transition, and is also called a critical point. So, if we are given a certain material with given values of T and J, all we have to do in order to find out the large-scale behavior of the system is to iterate the pair until we find the corresponding fixed point. Elementary theory. In more technical terms, Let us assume that we have a theory described by a certain function of the state variables and a certain set of coupling constants. This function may be a partition function, an action, a Hamiltonian, etc. It must contain the whole description of the physics of the system. Now we consider a certain blocking transformation of the state variables. The number of must be lower than the number of. Now let us try to rewrite the function only in terms of the. If this is achievable by a certain change in the parameters, then the theory is said to be renormalizable. For some reason, most fundamental theories of physics such as quantum electrodynamics, quantum chromodynamics, and electroweak interaction, but not gravity, are exactly renormalizable. Also, most theories in condensed matter physics are approximately renormalizable, from superconductivity to fluid turbulence. The change in the parameters is implemented by a certain beta function, which is said to induce a renormalization flow on the space. The values of under the flow are called running couplings. As was stated in the previous section, the most important information in the RG flow is fixed points. The possible macroscopic states of the system, at a large scale, are given by this set of fixed points. Since the RG transformations in such systems are lossy, there need not be an inverse for a given RG transformation. Thus, in such lossy systems, the renormalization group is, in fact, a semigroup. Relevant and irrelevant operators, universality classes. Consider a certain observable A of a physical system undergoing an RG transformation. The magnitude of the observable as the length scale of the system goes from small to large may be always increasing, always decreasing, or other. In the first case, the observable is said to be a relevant observable, in the second, irrelevant, and in the third, marginal. A relevant operator is needed to describe the macroscopic behavior of the system. An irrelevant observable is not. Marginal observables may or may not need be taken into account. A remarkable broad fact is that most observables are irrelevant, i.e., the macroscopic physics is dominated by only a few observables in most systems. As an example, in microscopic physics, to describe a system consisting of a mole of carbon-12 atoms we need of the order of 1023 variables, while to describe it as a macroscopic system we only need a few. Before Wilson's RG approach, there was an astonishing empirical fact to explain the coincidence of the critical exponents in very disparate phenomena, such as magnetic systems, superfluid transition, alloy physics, etc. Thus, in general, thermodynamic features of a system near a phase transition depend only on a small number of variables, such as dimensionality and symmetry, but are insensitive to details of the underlying microscopic properties of the system. This coincidence of critical exponents for ostensibly quite different physical systems is called universality minus and is now successfully explained by the RG, essentially by showing that the differences among all such phenomena are, in fact, traceable to such irrelevant observables, while the relevant observables are shared in common. Thus, many macroscopic phenomena may be grouped into a small set of universality classes, specified by the shared sets of relevant observables. Momentum space. Renormalization groups, in practice, come in two main flavors. The Kadanoff picture explained above refers mainly to the so-called real space RG. Momentum space RG, on the other hand, has a longer history despite its relative subtlety. It can be used for systems where the degrees of freedom can be cast in terms of the Fourier modes of a given field. The RG transformation proceeds by integrating out a certain set of high momentum modes. Since large wave numbers are related to short-length scales, the momentum space RG results in an essentially similar coarse-graining effect as with real space RG. Momentum space RG is usually performed on a perturbation expansion. The validity of such an expansion is predicated upon the actual physics of our system being close to that of a free field system. In this case, we may calculate observables by summing the leading terms in the expansion. This approach has proved successful for many theories, including most of particle physics, but fails for systems whose physics is very far from any free system, i.e., systems with strong correlations. As an example of the physical meaning of RG in particle physics, consider an overview of charge renormalization in quantum electrodynamics. Suppose we have a point positive charge of a certain true magnitude. The electromagnetic field around it has a certain energy, and thus may produce some pairs of electrons-positrons, which will be annihilated very quickly. But, in their short life, the electron will be attracted by the charge, and the positron will be repelled. Since this happens continuously, these pairs are effectively screening the charge from abroad. Thus, the measured strength of the charge will depend on how close to our probes it may enter. Hence a dependence of a certain coupling constant with distance scale. Momentum and length scales are related inversely, according to the de Broglie relation. The higher the energy or momentum scale we may reach, the lower the length scale we may probe and resolve. Therefore, the momentum space RG practitioners sometimes declaim to integrate out high momenta or high energy from their theories.